Oh, good morning. Jason Greenwood here, just checking in, turning on the webinar. I'm sharing my screen as well. This is just the front page of the webinar focused on field preparation, planning with AGI instruments and software. Feel free to ask questions as we go along. I can see a few are rolling in here just saying that you've arrived. So right away, I just want to mention that we'll look at first today is a seminar, a 3-day seminar here in Austin. And because this is about 30 minutes, I wanted to focus on topics that are most common, more geotechnical, for example. The site that we use for seminar near AGI has film material and a certain depth to bedrock, which is a common question. And the Austin area is a karst area, not super active, but it is a concern. So if you imagine all of the different subsurface imaging targets for the engineers, they may be given a site that, a certain area. And just to pull this up on Google Earth, hopefully everyone can see this. Let me double check. Yeah, okay. So I'm just going to go here. Just give you an example. Your task may be maybe based on exploration depth and area. This is North Austin. And this site in particular is undeveloped. There has been some earth moving, but you can see I'm just using, of course you could use GIS. There's much more advanced ways of doing this, but this is commonly available. So just to put this in perspective, if we were to run a line, this is a 2D imaging line, about that length, it would be 28 meters. So the one thing to consider is the size of your area. This is all pre-planning that you would do in the office for resistivity IP, SP methods. You'd maybe have a site map. You would also know perhaps that you have a system in-house. I'm going to go to these. This is our AGI website. And these system packages, or these are common. There's a lot of crossover between each one. Essentially, it's the switching system and the cables. And the rental pools at various rental companies, we also have one, or the product packages here are these two. This one here is the most common, the 56. This one is going to image deeper, of course, 112 electrodes. So you have to consider what has the what has been discussed as far as exploration depth and area. Here, this small area is about, let's say, not more than 30 meters by 10 meters. So it's somewhat rectangular, and they may have a footprint of a building, or they're curious. They may know from a neighboring building what the depth to bedrock is, and they're not sure here. And of course, if it's twice as deep, that's twice as much excavation, earth removal, and changes costing for the engineers. And so the idea is you reduce the amount of drilling to ground truth and cover a much larger area. Maybe just do 1 or 2 spot drills in there. So if we were to run a line, for example, if this is bounded by a fence, a metallic fence, that's something to consider. Like, can you see, I can see here that there's, well, I know ahead of time that there's not fencing here, but you also need to consider metallic interference in your line layout. If this red line was a pipeline or a fence, we would not want to run parallel to it. like this, because as we transmit on this end of the line, we may receive all the way at this other end of the line, and there's some 3D effect to the data. So the best way would be to run this way. As we're transmitting and receiving along that line, there's almost no effect of that pipeline or fence. So line layout's key, and considering obstructions. So in general, we have an idea for the site and the equipment available. In this case, for the seminar, it was 56. So we're going to assume that we're just checking out all of the equipment on the office side. It's best to do this before you deploy to the field and upload. There is a way to upload one command file, and this is the file that will tell the instrument where to transmit and receive. I'm going to make one really quick here and just walk you through it. Okay, so these are the electrodes that we would have at the surface, and then these are pseudo plot points, or these are our raw data. I've just typed in 56 electrodes. This is a dipole-dipole. The SuperSting is optimized for this particular array. It's the highest commonly used array. You can see this time estimate over here, 26 minutes. So this is purely for project planning. That's a key point. And the app that we have on an Android tablet, for this webinar, I'm not going to be sharing the screen from the app, but certainly you can see the similarities here of that screen as I pull that away. So that's the pseudo plot points there. Trying to get the glare off of it. So that's the same command file, same interface that we'll be showing on the screen here. And that's all with the Android app. So just using this SS admin program, it doesn't require a dongle or a license. It's a part of the basic utilities for the SuperSting system. I'm going to, let's see, audience view. There we go. I'm going to type in 56 electrodes. This is a new version which has been released on our website. It shows beta up here, but the one on our website will not say that. It's ready to go. This has the ability to make the other sizes of SuperSting command files and the very early one, and it has a minimum and maximum A, which is helpful for dipole-dipole. Prior, it was just the maximum A. So just a little heads up that there is a new version of SS admin, and feel free to email later. And this entire webinar is recorded if you had registered and are not able to view it. So this is very straightforward. This program ID is the name, and I'm just going to type in DD56. It's an R8 instrument. This create reverse array simply means it's going to start at the other end of the line. If I was to single step this, you'll see the blue and the red are the transmitter electrodes, and these are the 8 receivers. And one thing under the hood that is a little bit key here is that these receivers are not measuring on electrodes that were previously transmitters. As it single steps through, notice that we're advancing that transmitter and the receiver is always staying ahead of it. And if we were doing a reverse array, that would, let me have this go all the way through. you'll see it's doing the same thing, just in the reverse direction. And what that does is it improves the data quality. And these are things that we've learned over time. There's a lot of that in our design, and not all of it is apparent and described fully. But it is small, the devil's in the details, and these incremental gains are a big part of the company's engineering. And it all adds up to the ability to optimize for dipole-dipole, which is known to have slightly weaker voltages in some situations. So you need very clean connectors, low crosstalk. You don't necessarily need a lot of power. It's more about the receiver, the instrument. And when I'm talking about all of that, that's the supersting itself, the transmitter and the receiver in this device here. And there's also diminishing returns when it comes to transmitter power. 200 watts versus 300 watts is not the same as 50 to 100 for sure. And contact resistance. So we've kept things to a reasonable size on the transmitter, and then focused really on the receiver and the software and the firmware. So that's why it's slowly changed over the years, but not drastic increases in power, for example, because that's not the biggest gain. Okay, so here we're running a reverse array, and in roll-along surveys, this is where you pick up cables and advance them in a conveyor belt-like fashion. That reverse array will run slightly faster, but that's really the only advantage of running the command file this way or the other way. They're both 26 minutes. So if we looked, this is all pre-planning. We can see the site's fairly open. We don't have to go off in the brush here. That's 26 minutes. To put down 28 electrodes at 1 meter, this red line is 28 meters, that would take about 15 minutes in this open field. So for project planning purposes, you may know when you can show up on site. 28 electrodes, it's going to take 26 minutes for the machine. So you can definitely do probably every, if you're quick, once you get everything laid out, you can actually have 2 men pick up this cable and move it over, and not have to deploy again. So it's not 15 minutes every time. It's just the very first line's 15 minutes. And I would recommend for 56 electrodes, 2 to 3 people. And one of those people should be trained on data inversion, and the other 2 don't necessarily have to be experts on the processing, but someone should be able to do some field QC or be in close contact with someone on the office side to do that field QC. So for this particular line, you could run probably 5 to 10 lines in it, or this location, 5 to 10 lines in a day, no problem. And you could do something we call pseudo 3D, which would be, if we're running 1 meter inline spacing, running a parallel line not more than 2 meters away. So 1 to 2 times the inline spacing. And I'm going to show you 3D as well. Under Tools. So this is Earth Imager 3D, Tools, 3D Command Creator. That's a true full 3D array. We can change that spacing. All of this is hard coded into the command file, so it's different. This command file is created. It's critical that you have a good view of the site, because there's no changing geometry once you get to the field site for 3D. So you'll need possibly a laptop at the field, and if you want to adjust this grid, the numbers of electrodes in each direction, this code will keep things to that ideal geometry when you go to the dipole-dipole. And there's a paper by Jonathan Nyquist that focuses on the radial dipole-dipole. This one in particular is the highest resolution. I would suggest this one over all of these other ones first, and check that data quality to save time. If you notice, for 56 electrodes on this, it has 1,175 measurements, and it's taking 45 minutes. So, and here the simulation, you see their true cross line, but the measurements are in a radial pattern. And that optimizes signal levels. It brings you into signal levels closer to those of a 2D line, because these are many 2D radially measured lines essentially. And that's what that radial dipole-dipole is. And that's a paper by Jonathan Nyquist. Okay, let's see. Okay, so we're just planning, I got a question here about command file so far, so that's good. I'll make sure to cover that. This is still running in the background here, but you can see that 3D is taking quite a bit much more time, and is only, for these 56 electrodes at 1 meter, we're only imaging down 2.3 meters. That's our depth of investigation. This, if we were to do this 2D line, I'm just pulling up a calculator here. That's 28 electrodes. Let's say that we are running at 1 meter. So it's just 28 times 1 for the line length. If we were to take 22% of that, I'm going to take 20, be a little more conservative there, 20%. That's 5.6 meters of exploration depth. So in 2D, there's more bang for your buck, there's more exploration depth than with 3D, because there's costing to having 28 electrodes or 56, having all those cables, the manpower to deploy it, so that's a big consideration to doing true 3D, or what we call pseudo 3D. And in industry, I can tell you that they, after a little experience, they much prefer the inline measured 3D, which would be to do it piecemeal. There is a slight loss of resolution, but as long as you get the lines close, not more than, so if this was 1 meter, not more than 2 meters and parallel, measuring across, if you imagine a grid like that, the project is much more efficient. So with this one command file that we would be making here, we could do 2D or 3D depending on how many lines you measure. In this case, it's 28, which would be 7 minutes, which is even quicker, and it's 237 measurements. There's a backup array that I would recommend called strong gradient. In many cases, it's not needed, but it's very, very quick. In some cases, you may have a loss of data, and we'll get into that after we do our initial field setup. But I just want to let you know that this is the go-to array here, the dipole-dipole. If this is complete, there's no need for another array. Those other arrays, such as strong gradient or inverse Schlumberger, is similar to that. Those would fill in gaps, perhaps where there's data missing from the dipole-dipole. But if you have a complete dipole-dipole, there's no benefit to adding a lower resolution array. And there's a slight chance, especially in 3D, of actually complicating the inversion process, because you're adding data that's at lower resolution to highest resolution data and then asking the model to solve all of it. And depending on the numbers of measurements of the lower resolution type versus the high, you may have slightly less resolution. So it's always good to run a few lines if you're going to just run one array type and do some field QC. So this one we would call DD28. This end spacing, this is all on our website, by the way. I'll go show you this. I'm adding more and more. We're all adding a lot of the, there's a 170-page manual, and we're adding these details here. If I type in command file, combined command file, that's in here. That's with Earth Imager. It shows you, Earth Imager also has a merge function. If you make the command files all in SSAdmin, they'll merge together, or all in Earth Imager. Earth Imager has a slightly different format, merge command files. So that would be if you wanted to run dipole, dipole, and gradient. And just to show you that, there's this command creator, and it has several tabs. There's a surface tab. To do this 28, I would type in 28, 1 meter electrode spacing. I always suggest going with the default, which is 1 meter, so that you can use something we call scaling factor later. Because if I was to pre-hard code the electrode spacing at 5 meters and then apply a scaling factor later, it gets very confusing because it's a multiplier. But with a 1, you can run any spacing. So if your cables have a max of 10 meters, you can run anything from 10 and less by just typing in a scaling factor, and you don't need many command files. Further, the simulation tab here, this is survey time estimate. All of these settings are not in the command file. Those are set on the machine. So you don't need many command files for these different measure times or cycle times. Same here, this is a time estimate. And that's a question I get sometimes that the people will think, they'll change this and then they'll save a new one, they'll change this, save a new one. But none of that information is actually in the command file. Command files are human readable text files. You could open one up in Notepad if you want. Just checking in some questions here. Yes, with a true 3D array, you are limited to the grid size that you can form with that cabling. And as I showed here on 3D, this particular cable, I mean, typically, one that's very common would have a max of 6 meter spacing. So that's 78 meters by 18 meters. And that is the biggest array you could make with a 56 electrodes at 20 foot or 6 meter spacing. I'm setting the max N of 8, and then I'm creating this. And the max exploration depth for a common cable is 14 meters. But if we were to take that same 56 electrodes times 6, that's 336 meters long, and then take 20% of that, you can see we get down 67 meters. So this is estimated exploration depth. Your true exploration depth is dependent on the site conditions and the measurements you're able to achieve, but this is your best case, is 67 meters, and in 3D it would be 14 meters. So it's just that what you're doing is optimizing your resolution to near surface items and in that cross line inline area here. There's a lot more measurements, much denser. So if you have a small target, in the near surface and you have the cables, I would definitely recommend 3D. But it's what you need to consider is your exploration depth and your production. Like how much area do you need to cover? Like this, if we needed to cover this whole area in true 3D, it might take 2 or 3 days. But in pseudo 3D or inline space 3D, we could do it in a day, maybe, if we worked really hard. Okay, so that, just trying to answer that question about 2D and 3D. That was since, okay, so for a 3D array, do we have lines close to each other and the depth of investigation is less than for 2D? Is it better to run 2D lines in a grid and then interpolate the results? Okay, none of the results are interpolated. We're actually solving a model for the data, and there is some 3D information in a 2D line. So that's important. It's not interpolation like contouring or gridding. There's none of that. This is solving a model for the 3D data that is not solved for in a 2D line. So that's that question. And just to show you here under tools, combine parallel 2D lines. Our units meters. Let me just a second here. I have to find this. That's a different data set. Combine parallel 2D lines. That's under tools for 3D. Okay. This DD2D is at 0. And what I'm doing is I'm going to load, we only measured one line. That's how, but if we had measured multiples, we could do this. So I'm just copying this in 3 times. And what it'll do is any one target that's in the subsurface will become a cylinder. So again, this is data from here. And okay, so the spacing 0, 1, 2, 3. Let me fix that. Okay, so this information in between the lines is now solved for in the model. That's our raw data, the grid. And when you're transmitting on this end of the line, as you would see here, once we get to the other end of the line, so these data here, the y direction is infinite in a 2D model space. Let me close this in here. So this is that same line in 2D. We don't solve for this 3D information. That's why measuring a 2D line parallel to a metallic target causes an issue. But in here, because we have a 3D space, we're solving for that. And it's testing all the different, it's an forward inverse step, it's testing all the different material properties that would give you this raw data here. And that's in these iterations. And that's more a topic for the seminar. But yeah, it's not interpolation. It's actually solving the inverse model for those parallel measured 2D lines. Um, so so we have an idea for the geometry and what we can do here, what the exploration depths are. And in this case, we're going to say the target is depth to bedrock, and any moisture which may impact the foundation design. And this is all hypothetical that there would be some kind of construction project here. So in the 2D data, let me actually, at this point, let's say that we have our plan. We're going to do several 28 lines, and then we'll do one 3D grid here, a tight one. And in this case, it's going to be a time lapse, so that'll be interesting. There's, just make sure I'm keeping up with these questions here. So there is going to be a time lapse. Yeah, okay, so someone asked any automatic acquisition functionality considering repeated survey time lapse. Yes, there's a logging function built into the SuperSting menu for short-term time lapse, in that you wouldn't want to leave it out in the to the elements with the cables exposed and that type of thing, because typically for time lapse that's going to go over several days, you need to protect the cables from rodents or anything that may go on site and chew on them and that type of thing. Oftentimes they're shallow buried or they're in boreholes. And then the instrument itself needs to be powered by something that will not, the power won't draw down. And we do have a remote monitoring accessory that will handle that, or you could stay on site for the SuperSting to make sure that it's safe. But that logging mode menu was added for submarine groundwater discharge, which would be one tidal cycle, which may be 5, 8, 12 hours. And so you would leave a marine cable out, which is much less likely to be damaged, like on a quiet beach setting with sandbags over it. And that's what that functionality was added for. So there is built-in time lapse on the SuperSting itself. Okay, so we haven't, and that was, is there built-in functionality for time lapse? Is rebar in concrete pavement enough to impact parallel resistivity lines? That's a tough question because sometimes the rebar is all tied to each other in a grid. So if you imagine a metallic mesh, and that gives, even though concrete is resistive, that makes the concrete overall very conductive. Parallel to a concrete pad is generally not an issue because it's diffuse and that it's not like a pipeline, like one linear conductor. It would tend to show up as slightly lower resistivity in the near surface. So if there was a pad parallel to a line, I would try to run perpendicular to it. But again, that pad is probably thin and like a pavement is very little impact. So there's a lot of data collected parallel to roads, which are concrete, and there's no issue there. Sometimes they even run on a crack or an expansion joint. They put the electrode through that into the subbase, and there's ways of coupling to the subbase through concrete that has worked quite well. And if you happen to hit rebar, you can even put a plastic pipe or sleeve of some kind to insulate the electrode from that. So there are case histories like that. The issue of running alongside roads is that they're common places for utilities, pipelines, and conduits, and those are the concern. It's not so much the road. The road would have a very minimal effect. That rebar that's in the concrete road would have very minimal effect If you're running parallel to it, if you're running through it, as long as you avoid not directly touching the metal, there's case histories that show good ground truth correlation when they're measuring through reinforced concrete in a thin layer at the surface, as you would have in a road. But again, roads are, it is always best for consulting to do something along the lines of a EM mag survey, or look at as-built diagrams, or have a utility location map. So that question was, is rebar in concrete pavement enough to impact parallel resistivity lines? And I would say that it's pretty safe. Watch out for the utilities though. How useful is it to combine 2D resistivity and IP data for saline groundwater exploration? That's a good question. Again, it has the same command file. The same command file can measure IP or resistivity. It's a machine side setting. So none of this information is set. All this is doing is letting you know that your measure time doubles for project planning purposes. So if you're going to measure IP, you need to be very sure that there's actually IP targets at your site. So this question is IP useful for saline groundwater exploration? And I would say that really what you want is resistivity, because once you're below the water table in 100% saturated portion of the aquifer or the subsurface, your dominant control of resistivity is pore water conductivity, porosity, those two first things, because you no longer have moisture content to worry about because it's 100% saturated. So if you have an idea that you're in, for example, in West Texas, the exploration for saltwater, and I'm going to show you a case history here, is resistivity alone. The IP would have taken them a lot longer time, and you can see, like in West Texas, they would run 112 electrodes like this. It's 1 hour and 17 minutes to do the command file. It's very, look, you can see how dense this data is. This is 112 electrodes. They're exploring for saline water there, for drilling muds and things like this. This is a question coming in here. Okay, so 101 hour and 17 minutes with resistivity alone. It would be 1 hour and 54 minutes of just machine time to measure IP. So, and I know that there is clay layers of interest in the near surface, but that may have higher chargeability, but that's not the dominant target. The target they want is the salt water. And that case history is here on our website. Under case histories tab at the top. I'm just going to scroll down. There we go. So this blue, this low resistivity feature, is the higher pumping zone. They know the approximate depth to water here, but they're getting variable pumping rates. In here, it would be significantly less than 100 gallons per minute. And as you can see, there is a somewhat of a vertical feature here, and that's related to fractures or increased porosity. There's water all through here, but the highest pumping was here. So this geophysics saved them drilling cost and pumping cost. And also there's this high resistivity zone is thought to be possibly voids, because it's above the water table, and also significantly higher resistivity. So there's some knowledge of this area in West Texas from drilling records, and so they know when they see this pattern that they're looking at potential cave-in hazards or loss of mud circulation, and then this is an area where they would want to get that saline water. The regulations are such that they preferentially target saline water for the muds versus the potable water, which would the agriculture and community would want. So another thing about interpreting these data is these numbers over here shift from site to site. It's site specific. So what is considered a hazard for a void at 273 ohm meters in this particular area would not be in an area of Kentucky or another karst area. They have these karst targets shift around, and in targets in general don't have a specific resistivity for a material property until you have ground truth to adjust your interpretation. So what we're looking at here is an image and the patterns mainly, and then we have some knowledge of where they previously have encountered voids in the region, and what this particular lithology's resistivities are. And once you know that, it vastly improves the speed at which you can interpret additional lines. Okay, so we are good to go. As just shifting back to this planning, we're good to go here. We have a 56 electrode system as described here on our website. We're going to be powering it by a generator, and that's a nice, this is a Honda. This is the main and boost power supplies. This combination of equipment is about 27 pounds. It's significantly lighter than deep cycle marine batteries. Just going to show main and boost. That's our test box. You don't have to worry about charging it overnight. Those are the connections, same connections you would use for a battery. If this would be with a main battery and the boost battery. If you were to go to our website, the help desk, and type in battery or AC supply, you could get information on what's recommended there. So that's just power. So we've taken care of that. We've saved a command file. There's two ways of uploading that command file, and if we had a 56 electrode command file, we could handle any numbers of electrodes less than 56, and that's what I would recommend. There's a function called end address, and so you don't need, if you're going to run 28 or 32 or something like that, you don't need those command files written unless you plan on doing roll along, and that gets much more complicated. But that 56 electrode command file will handle everything. There's also a video here for making a command file and the settings, just as we had showed there. A little bit of QC on the instrument. If this instrument was shipped to you, you want to make sure that it's calibrated, everything's functioning okay. There's a receiver test, and that is, this is the procedure there. There's a box that comes with the Super Sting, and you just plug that port in that says receiver test, and there's calibrated resistors in there, and we would like to see plus or minus 5% from that 500 milliohm range. And that lets you know if it's transmitting and receiving okay. there's an additional test called the relay test, where you would plug in the switch box, and that is in this video. I think if I find, yeah, right there. Okay, so that is the switch box, and you can see this yellow cable going and plugging in here. That's the, on our new systems, there's this adapter box, and that, let me zoom in here. That port on the lower left is the receiver port. Any one of these upper ports, if you plugged it in, would give you access to these manual wires. And then this port is a IP test. If you were to run one extension to this port and another extension to this, and then to your automatic switching, your multiplexer here, that, and then this is your passive cables, and you can see an electrode installed in earth there. If you were to pass through that upper port, you could run an SP survey, and that is measuring just the background voltage along the line, and that's indicative of pore water transport, you know, a charged ion moving through a pore space, and that is displacing voltage, and the SuperSting measures that. So that's not an imaging method as deployed in just a simple 2D line where you scan the voltage down the line, but it would indicate where you might have preferential seepage, and I'll show you that in 3D as well. Okay, so we've QC'd the instrument, and we're ready to deploy to Earth. Here, roll along setup. This video actually shows. So from the, let me just pause this right in the first screen. Okay. The SuperSting in this case has a command file. What's shown on the screen here would be what you see when you create a data file. And I just want to show you that end address function. See if I can expand this. Okay. Okay, in here there's create data file number 2. There's automatic mode prior to this when you turn the instrument on. We're going to create a data file 2. We're going to type the name in. Let me make sure you can see this. Okay. And in this case, we're just typing in 3. These are the command files, and the negative, okay. We selected a command file there. It's DD56. In this menu, we're choosing measure units meter, scaling factor. And that number there is what gives us the ability to change spacing for any value that will hit your cables. And that saves you quite a lot of time. And then this start X, Y, and Z, I always suggest putting zeros in here. 0, 0, 0. This next question is roll along. In this video is focused on roll along, but we're going to say for the majority, no. Roll along is this conveyor belt movement of the cables. Edit end address. That is where you would leave it blank if you were using your full cable set, or something less than the max. And that number you put in there is what you measured up to and include. So from here, this is 56 electrodes. If you wanted to measure, you know, you would just coil up the cable that may be not used and just install a portion of it. And you don't change where the switch box is. In a 56 electrode array, the switch box is always in the middle with 1 through 28 on a low address port and 29 through 56 on the high address port. So if you were going to run 50, you would just have that high address not fully deployed. That's critical. So then we go through these. Just showing that, changing that. And in that case, it's off. Then enter to continue setup. Here, there's switchbox or dual mode Swift. Now, even though if you had put end address of 40, something less than 56, you would still say that you have that switchbox and that it's the full size because your command file hasn't changed. This is, an 8-channel instrument. And here, see it says switchbox 56. If we were using end address, we'd still say we were using that. And then there's a cable address table, and that needs to match your command file. And that is blank here. Oh no, he's actually showing you how to add the switchbox, which is the positive and negative keys. Here is the cable address table. This is menu 622, and it's going to be set up in the sizes that are being rolled, but in the minimum size here is just what's on the low address and the high address. So it could be 1 through 28 as there's electrode low and high, and then as section 1, and then section 2, 29 to 56. And you don't need to edit. Here he's entering it in 14s because he's going to do 25% roll along. That's a lot more keying. You don't have to enter your smallest cable section. And this gets into roll along, but for non-roll along, you don't need all of that. This is factory defaults, and okay, so he's actually he's measuring on a little test box here, but I just wanted to show that end address function to let you know that it is possible to do all of the surveys with one command file. So back to this site, we're just using one command file. We installed this line. We've QC'd it with the receiver test and the relay test. Let's see what that data looks like. This is the DD28. And what I've done is, this is the raw data as downloaded from the SuperSting for this particular site. And we can see that there's a smooth pattern. These are commonly accepted ranges. This is surface defaults. This is Earth Imager 2D. This is something you could do at the truck. If we click this button here, this pulls up our initial settings. These are commonly accepted voltage ranges, repeat errors, and ranges of raw data. These data are not interpretable beyond very simplistic patterns that there is lower resistivity in the near surface, higher at depth, and they're smoothly changing. To show you what some more problematic data would look like raw, these data were collected. So you can, let me show you, this is actually a partial collection. I'm going to change from meters to electrode number. This is 49 electrodes. So that's an odd number of electrodes. It's actually a switchbox 84, and the full 1 through 42 is collected, but the 43 through 84 is only partially deployed. So they used end address. Now what you see here, I'm sure many of you would recognize a spike on the low address portion. That change from 13 ohm meters to 310 ohm meters in one pseudo plot point is clearly a spike. So that would worry me, and I would start looking at the other lines and inspect the cable. So this is the first one. Let's look at the second one. more spikes. Look at the third one. Same spikes in the same exact area. That is clearly indicative of a problem with the connector on the cable. And when I see noise like this, 9 times out of 10, it's the most simplistic thing in the system, not the settings of the supersting, not site conditions. It's the connectors and the cables themselves. So that if you notice those spikes there, that's not something you would see from a pipeline, which would give you this V-shaped, we call it, they're pants legs or inverted V pattern. Let's look at another one. Again, that area has spikes. So let's load the first one. And we'll go to initial set. We'll enable spike removal. And then look under edit data editing statistics. So there's 4 singular spikes. Not too bad. These data are usable. Yeah. So, but it is telling you there is an issue. And from talking to the end user, they told me in this case the low address portion was a third-party cable. It was colored red. It's a non-AGI type cable with a different manufacturing method, so a third-party type of cable, and those are known to have some issues like this. So you can see those in the raw data. Once you go to invert it, I'm just hitting the inversion. It's at 9% RMS. If we right click on the cross plot, you can see these outliers in the data. This data does need to be cleaned up, and there is a way to do that. I'm just hitting the left and right arrow key. And then I'm going to run another model. So you can see some data is missing here over those spikes now. So there's a little bit of a gap. In general, the pattern has not changed from the very first inversion to this one. So that's good. That's an indication that it's not a very noisy data set. If each new model after a 5% RMS histogram removal doesn't drastically change this structure here, you would be more comfortable with these data. Now the RMS is 2%. Very good fit. So it's definitely usable, excellent data, but I would really watch out for that third-party cable there. One common way to look at these is at 1-to-1 ratio in the unit you're interested in. This is probably, okay, so they're running in meters because I can see 9.84 feet, 3 meters, okay? And then you need this clipping boundary, about a 45-degree angle is common. Without topography, a 1 will give you that. See, there's no resolution here. We don't want to show this portion of the model space. That's not a real target, and this as well. So that's why that's clipped off. And then I would suggest showing the full range of color unique to each line, so you see all of the changes here. When I mouse over these different targets, if you look in the lower left corner, it tells me the resistivity, the depth, and the line meters. So that's our 2D. This site, let me go back here. Let me just show you. This is the line itself. Laid out. There's the generator in the middle. This is fill material, and then there's depth to bedrock that is known. This blue area here is the fill material in the left side, and this red this is our depth to bedrock right here. And these changes down here are related to different layers in the limestone that have more clay in them. Marine, I'm not, my geology here is not, I don't know the name in the Edwards limestone, but I know that there's alternating mudstones that have more conductive minerals and electrically conductive minerals in them. And that's why we're seeing that 50 ohm meters versus 100 ohm meters there. But this change from 12 to 22 is related to fill material. So that's our depth to bedrock. And then this is more of a fracture. This is also fill material up here, but it's significantly drier and more granular. You can see that at the surface. And this is related to a spring. So there's some moisture. And at different times of year, it'll actually become blue down here as well, when there's high runoff. So this would be something to consider for drainage issues. You can inspect that, or this would be a drilling target, and then maybe a CPT here to confirm that. But that's what you can get from 2D. Let me just go through the questions here. Useful data, can you collect useful data beneath a plastic liner over filled cells? So plastic, of course, is an insulator. There's a leak detection method. There's an ASTM guideline where you place one of your transmitter electrodes outside the liner and one in a pond, and then you measure the potential across the pond, and any small pinhole leak in that plastic liner will show up as a voltage anomaly, and you can map that as a contour map. It's a very straightforward leak detection method that utilizes the insulation of the plastic. So that's answering a question. It's not getting specifically if you could measure beneath plastic. To measure beneath plastic, you would have to somehow transmit in that material. And so if the electrodes were above it, it would not give you information unless there were a significant tear in the plastic. You would show up, the data would show up as a very sharp, high resistivity layer and nothing beneath unless there was a tear in the plastic. So as far as subsidence and issues where you don't have a tear, you could not transmit through that plastic insulator. There's other methods that you would focus there. A very conductive surface. That's a good question. Any recommendation in case of very conductive surface? This data here from our field site is surface data. See the surface defaults? If I was to go to the Earth Imager C drive, this is the demo folder. There's a data set I actually collected a long time ago at USGS in Florida. Now, if I was to load this, it's actually in Tampa Bay. I get this big error. 86.6% of data is to be removed because I'm applying surface defaults. There's some clue in the name of the file, but it would otherwise filter all of the data out. This is the only portion of the cable which was on land. This is a cable that went from land over a seawall and then underwater. So amazingly, it actually is able to solve it. But what you need is conductive earth defaults. And I've selected that, and that changes these ranges of acceptable voltages. Marine data tends to be much lower. This would also be the case if you were in a brine saturated dry soil. Those are more rare. Typically the most conductive areas are marine saturated near shore like this. So if I was to load this data again with the conductive earth settings and process it, you see this 0.23 ohm meters, 0.23 to 0.93. That, and it's smoothly changing. There's only one spike. You do not want to use conductive earth if you have noise, like we did before, because then you're just going to fit for noise. It needs to be a true conductive earth setting, like this beach where the cable is going under salt water. So that's something to watch out for. You see here 0.23 to 59. You may have that if it's only due to very conductive spikes, and you'll see those clearly. But here, this is a smooth gradient, and there's significant amounts of data less than 1 ohm meter, which is when you want to use conductive earth. And it even says that in the drop-down menu, less than 1 ohm meter in the raw data. An example of data where you would not want to apply it, where you would want to filter that data out. I believe these data have some spikes, not enough, but they would look like that. So this range is still 12 ohm meters, but it could go down to 0.2 ohm meters because of these little blue spikes, but it's not a true conductive, it's a dry area. But back to this this marine data. That's a spike, and we can handle that with spike removal. And you can see almost all of the data is retained. That spike is related to water moving across the cable. There's a reasonable fit here, but we need to add the bathymetry and the topography from the land portion. And that's a special file here. It's nothing more than 2 arrays with bathymetry, topography, and water conductivity in it. And that you make for post-processing. Okay, and there we go. So that's answering that question. I can see there's one. Let me just see if I can get through the last of this. Reducing contact resistance on electrodes when surfaces in dry and sandy soils. That's a good point. Contact resistance is your primary control on how much current you're injecting, and lowering that contact resistance is critical to quality data. If your contact resistance is below 1,800 ohms, you can use boost mode, and that's purely based on the impedance. Even if you had a power sting, you couldn't transmit through some contact resistance. So lowering it is always best. Salt water, 2% salt water is a good method that may drain quickly. You can add some bentonite, powdered bentonite to it, and make a bit of a slurry. The bentonite itself is conductive, and you wouldn't need the salt, but you certainly could have it as well. So that bentonite can be messy. There's a drawback there. So if salt water doesn't do it, then go to bentonite. There's a question about injecting current. Which should be injected? Current time of 0.81, 1.2, and so on, used to attain good resistivity data. The default is 1.2 seconds. The only time you would want to run longer is if you have an incredibly noisy area that you just need to measure over the noise and smooth it. That's very rare at industrial sites. The idea is to measure 2 quick measurements and compare the standard deviation between them. And that's 1 to 2 seconds. That's why we chose that. The 0.8 seconds may not have enough charge up time if you're doing IAP, but the default is 1. The time savings between 0.8 and 1.2 is less than a minute. So I would not stress over that. The data between point A to 1.2 is usually insignificantly different. You would have to, in order to know at each site, you would have to measure one completely at point A to one at 1.2, which is somewhat a waste of time. There is one last thing I would suggest if you have the time, not to experiment with the measure time, and that's to run a reciprocal measurement. And that I would just do once, and that's a special command file. In this case, I would call it DD28R, and I would include reverse array. We're going to change the terminology of that to call it a reciprocal. And what that does is it measures transmitters and receivers down the line, and then it swaps the source and the sink and measures the same data. And by the theory of reciprocity, that would give you the same V over I for that measurement. So here you see it going in the normal, then it's going to come back and measure the reciprocal. And you can look at a new plot in Earth Imager. In this case, I'm just going to look at apparent resistivities or repeat error. You can see the error is slightly higher here, where the water was sloshing across the cable. That's, if you saw that in a non-marine data, you would be concerned. Reciprocal also will help show you these point plots with percent error, and you should see just a Gaussian or random error, and less than 10%. But if you see spikes around a connector or other portion of your cable, it indicates there's probably a problem there or something specific about the site. So if you wanted to QC your cables in your system, go out to a known clean site, maybe near the office before you deploy, and just run a quick reciprocal test. So that is, I believe I have all these questions here covered, and we've definitely run over in time. So thank you all for attending. If there are any additional questions, just send them across now. There will be an email with this video. We didn't really have time to go into 3D exactly, so I just showed you from this site the depth to bedrock, the clay layer, the drainage. This is where the spring is that tends to drain down the hill. So this is just just touching the surface of how roughly you would plan a geotech, more engineering focused type project, and exploration depths, 2D, 3D, contact resistance, menus, and then trying to point you towards this help desk, which has more and more information. Like if I was to type in contact resistance, which is that last question, it would point us towards all of the things that are related to contact resistance. Yeah, why you might get HVOVL. That can happen for many reasons. There's troubleshooting here, and that's all at the help desk. So thanks again for attending, and we'll catch up with you next time. Thanks.